Okay. Let's go from current slide. All right, we'll do example 4 here. But before we do that, there is an announcement, and you are exactly the type of target audience they want to hear this announcement. A couple of local schools, as in it's Bree, right? And huh? Caitlin, I thought so. All right. Anyone else coming since the call roll? A couple of other local schools, UAB and Tuscaloosa, have had these programs in the past. They're NOIS scholarships. Okay. They are a National Science Foundation sponsored program, so they have plenty of bucks. Schools apply for them, compete for them, and like I said, UAB has had it, and Alabama's had it, but they're only 3 to 5 year programs. I have a feeling theirs are ending, but another, not so local, but fairly local school, Alabama A&M, has now been chosen to be the North Scholar School. So what they do, they are recruiting from people in science and engineering majors, anything, math, science, engineering, anything in those majors. They invite you to come to the campus. They pay you to be there. They usually house you. They usually feed you. They usually provide transportation money to get there and back once. They don't do it for every weekend. Usually it's sometimes 3-week programs, sometimes full summer, like 9-week programs, something like that. I don't know what A&M's is, but they are usually really nice deals. And you learn an awful lot. You get to tour research facilities, you get to do things, you get to tutor kids in high school, and it just is a very, very, very positive experience. Okay? What they're trying to do is convince people that maybe if they get into their upper level courses and they find that pure engineering or pure science really may not be their bag, to think and say, hey, but I can always teach. Because they want people good in science, good in math, to be teaching science and math. Unfortunately, our K-12 education is really hard for them to get good math and science teachers in the high school and even lower schools. So they, whether you're even thinking about it or not, if you want a good summer that they're paying you to do it, look into it. I would share the link with you, but every one of you got this email. It says to all students at lawsonstate.edu, you got this email. Check it out. Okay, it's on the Alabama A&M North scholarships. Okay, it's usually a really, really good deal, and we've had several students go to it. I think maybe some of them have gone into teaching, others have not. That's fine. They're trying to reach out to as many as they can. But every student that I've heard of has had a very positive experience with it. So please give it a shot. Consider it. If you didn't have plans for the summer, didn't have a job, this will count. I mean, because they pay you pretty nicely to participate. All right. Now said there, any questions on anything we've done so far? Were there any questions that you want to hit now before we get started? Okay. If you run into any questions, please ask. Okay. We had skipped example 4 by mistake last time, so they're on page 301. We're in chapter 4 still, trigonometry, 4.5, graphs of sine and cosine functions, and we're on example 4, the bottom half of page 301. So let me get my pen set up, and we will do example 4, which should be easier than example 5. We'll see. In some senses, I know it is. All right. Analyze the graph here. Y is equal to 1/2 sine of x minus pi thirds. Okay. Okay. To start a problem like this, I always start with the parameters. Okay? What's the first number you see? 1/2. What is that? What do we call that? It's a fraction. Very good. Okay? What in position of a sine or cosine function? What was the -3 up here? That's the a. So a is equal to 1/2. Now what does a relate to? What characteristic of the graph? The amplitude. Perfect. So the amplitude is what? It is also 1/2. It'd be the absolute value of a. Well, a is positive, so it is 1/2. Next number you see or don't see, what is that? 1. And what do we call that one? It could be out here too. B. B is 1. What does that relate to? The period. And what is the period? No, it's period is 2 pi over b, 2 pi over 1, which in this case would be 2 pi. Okay. Now, as soon as I get the period down, I usually go straight for what next? The interval. What is your interval? The book doesn't do this when I do it. It's a quarter of the period, which would be, in this case, pi halves. Though it may not be. We'll get to that later. What's the next number you happen to see? Oops. Is pi thirds. Now notice he didn't say negative pi thirds. And the reason for that is it's usually x minus c. So yeah, pi thirds is the correct answer. What do we call that? What does that relate to? What does that relate to? Say again? I can't hear. Huh? No, that's what the B would have been a stretch. It wasn't. It's 1. C is a, remember, when you add or subtract to the function, that's a vertical shift or translation. When you add or subtract to the x, that's a horizontal. And what is this?
Horizontal shift.
Say again?
Horizontal shift.
Horizontal shift which way?
To the right.
To the what?
Right.
Right. Correct. Okay. That's because, remember, x's are always backwards. Okay, so this is a right shift by 1/3. So that we call a phase shift. Phase shift is pi thirds. This introduces a little bit of a problem. We're wanting our interval to be pi halves, but the phase shift is pi thirds. So that means we have to settle on the least common denominator for our interval. We're still going to use the pi halves interval, but for our drawing of the graph, we're going to have to use pi 6. Okay? This is Dimitri. If I can find, there you are. Hiding. Okay, does anyone else come in since I called roll? Okay? So what I'm going to have to do is find the least common denominator between these two, and actually my drawn interval is going to be pi 6. Okay, because I've got to be able to find my pi halves and my pi thirds. And if I just drew pi halves, I wouldn't be able to find pi thirds. If I just drew pi thirds, I wouldn't be able to find my pi halves. So I'm going to draw it in 1/6 of a pi. But my interval is still going to be pi halves. I don't know if that's making any sense, but we will figure it out, maybe. All right, that took up a lot of room. I wish I'd have written it up here. I'm going to do my graph down here then. I don't need that line up there. Let me take it away. That's just ugly. Okay. All right. I think I can. Well, okay. So I'm going to start ticking off points on the horizontal scale, remembering these are in 1/6 of pi's. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, -1, 2, 3, 4, 6, 7, 8, 9, 10, 11. Okay, something up there. Now, vertical scale, what do I need to be doing? What do I need to pay attention to? The amplitude. So all I need is 1/2. So I'm going to do that as plus 1/2 and minus 1/2. Obviously, I'm not drawing this to scale, okay? But I'm drawing it so I can read it well. Okay, so I'm going to label these. Pi sixths, pi thirds, pi halves, okay? 2/3 pi. I'm not going to do this for all of them. I'm not going to do 5, 6 pi. So 1, 2, 3, 4, 5, 6. That would be, excuse me, that would be pi. 1, 2, 3, 4, 5, 6. That would be 2 pi. Okay, this will be minus pi 6, minus pi thirds, minus pi halves, minus 2/3 pi. 1, 2, 3, 4, 5, 6. This is minus pi. 2, 3, 4, 5. Somewhere out there is minus 2 pi. Okay, I've got them labeled. Only reason I'm doing pi 6 is I've got to be able to plot my pi thirds because of my phase shift and my pi halves because of my intervals. Okay, so remember those are 6 of pi's. So where do we begin? Even though it was the last thing we came up with, it's the thing we start with. See, that tells us where we start. We start right here. And where is sine at this initial point? Where does sine usually begin? Second? At the origin, except it's going to start here at 0. So this is going to be our jumping off point, or jumping in point, or jumping up point, or something like that. Okay, that's our starting. Now remember we're in pi sixths. Our interval is pi halves. How many 6 of pi's does it make to make a half a pi? 3. Okay, so what we'll do is 1, 2, 3. This is going to be my pi halves. Okay, it starts at the origin, and then in one interval goes up. 1, 2, 3, back down to 0. 1, 2, 3, down to minus pi 1/2. 1, 2, 3, back to 0. That doesn't even look right, does it? Okay. My spacing is not great. That's another way of saying it really stinks, okay? But we won't say that. Let's go the other way. 1, 2, 3, that will be a minus pi 1/2. 1, 2, 3, a 0. 1, 2, 3, a positive 1/2. 1, 2, 3, another 0. Okay, so here's approximately what our graph is going to look like. And obviously my spacing is really lousy, but that's generally what it is. Okay? You start at the phase shift, and that you treat as the origin now. And then you do your interval to the right, and remembering that your sine goes up, back to 0. It starts at the origin of the x-intercept, and then you go up to your max, down to your intercept, down to your min, up to, that's how sine goes. And this way, opposite of that. Down to the min, up to the intercept, up to the max, down to the intercept. That's how sine operates, going one interval at a time, but because we had a phase shift to thirds, but the interval was in halves, we had to do 6 so we could count for both of them. And that's why we did it this way. Okay? Have some weird positioning there, but it works because that's what the intervals tell you. Okay, does that make sense? Everybody see it? Any questions about it? Start at the phase shift, then from there, count your intervals, keeping up with which trig function you got. Sine is going up or down, where is it going, and how high it goes, that's your amplitude. 1/2.
How did you know how to use pi 6 again?
Okay, well, because you had an interval of pi halves and a phase shift of pi thirds. If I just drew pi halves in here, you'd have to guess where pi thirds was. If I just drew pi thirds, then you'd have to guess where pi halves was. So I take the least common denominator between the two. That would be 6. So I do my pi 6. I don't ever use pi 6, but I count off 3 pi 6 for my interval because it's pi halves. But I had to find that initial place at pi thirds. Didn't quite hit it well, but came close. Good question. Any others? Does it make sense? All right, good deal. Pretty exciting stuff, isn't it? Let's see how the books look. Oh, look at that. They made it look pretty good themselves. Okay. There is a checkpoint here. Highly recommend you do the checkpoints soon after you leave class. Okay, we already did example 5, so we'll just walk through that. Don't talk anything about it because we've already done everything with it, including drawing it. I meant to say on the book likes to do those little table-like forms, and sure enough, each of those points were on there, but you didn't even have to identify them if you just plotted them right. Okay, so that was example 5. Now what is next? All right, yeah. I think this is where we pick up here. This is middle of page 302. Yeah. The final type, they don't say this exactly in the book, but it's here. The final type of transformation is the vertical translation, shifting up or down, caused by the constant d in these equations. And why in the world they write it in the front, I think I might have a guess, but it seems sort of dumb. If I were writing this, I'd say a sine x, b, I put b on the outside, x minus c, not the same c as theirs, close that, plus d. Now, I guess so they are afraid you'll think that plus d is part of the sign argument, even though it's not in parentheses, they put it in front. But then later, in an example, they'll put it in where it belongs, so I don't know. But that d is your vertical translation, okay? This is centered normally at the x-axis. You go up and down from the x-axis. This moves you up d units. Now you go up and down from y is equal to d. I call d your equilibrium position. Okay? You go up and down from the equilibrium position. That's what the physicists say. So the shift is d units up for d greater than 0, and d units down for negative d. D is less than 0. In other words, the graph oscillates about a horizontal line, y is equal to d, instead of the y-axis. That is what I was trying to say. Okay? So A refers to the amplitude, B refers connected with the period, C is your horizontal translation, phase shift, and D is your vertical translation. Okay? It doesn't have a special name. Okay. Oh, and they skipped the example. Good for them. Okay? This is example 6. So let's see if we can find some space to write. That looks like a good space to write. All right, example 6. Sketch the graph of, I'm going to write it up here this time, y is equal to 2 plus 3 times the cosine of 2x. Okay. Let's start identifying some values here. What value do you see?
D is 2.
The D is 2. And what does that relate to?
Vertical.
This is your vertical shift, Vs, okay? What's the next? A is 3, and that relates to the amplitude, and the amplitude would then be 3, okay?
Didn't you say if A is negative, the amplitude is going to be the opposite? Amplitude is going to be positive, right?
Okay. What the negative does in front of the amplitude is a reflection across the x-axis. So yeah, you start down there rather than up here. Yeah. Or for a sine where you start at the equilibrium point, you go down rather than going up. So yeah, that's what a negative A would do for you. Okay. Amplitude is still 3, but you start off going downward rather than upward. Okay. Well, the cosine, you would start down and move up. Yeah, something like that. Okay. Next. 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 It's the next number you see. The second 2. And what is that? B is equal to 2. And what does that refer to? The period. And how is the period connected to B? What? 2 pi over 2. 2 pi over B, which is 2. So that would be simply pi. And what's connected with the period? Your interval. And what is your interval then? Pi force. Perfect. And this one, the C out here that you don't see, is 0. Okay, C is equal to 0. There is no phase shift. So this is going to start where it would normally start as a cosine function. All right. So now we draw our axes. Okay. All right. I'll tick off a few points. Get out of there. Okay. Now, where do you begin? Where do you begin? Second? Okay. Not yet. Again, if you had a C in there, phase shift, you need to start there, but you also have a D, so even though it's the last thing to cover, that's where you actually begin. Your C is 0, so you're not going to shift horizontally anywhere, but your D is going to move you up to 2. Now, I like to go on and draw a dotted line in there to remind myself that's my new equilibrium position. Okay. Now, what function are you dealing with? Trig function. Which one? What trig function? Only dealing with 2 of them right now. Which one we got? Cosine. All right. Boy, that was the hardest question of the day, huh? Okay. Where does cosine usually begin? Where does cosine usually begin? Second?
The point before it, right? Number before? The answer.
Okay. A regular old cosine graph, where does it usually begin? At 1, okay? Or, since we have an amplitude here, at its max, because 1 is normally the max. So it starts at the maximum. What is our maximum here? 3. But your equilibrium position is 2, so you're starting 3 above that. 1, 2, 3. You're starting up here at 5. That's where you begin. If you had a phase shift, you'd be right or left there, okay? But this is starting at your maximum above your equilibrium position, which is given to you by D, and it's 3 points up from there because it's a cosine function. Okay, no horizontal phase shift, so we don't have to worry about moving right or left. All right, now from there, we now measure our, and we could have done this to begin with. Oh, I didn't label these. Sorry about that. This is pi force, pi halves, pi, 1, 2, 3, 4, 2 pi. Okay? And to the left is minus pi fourths, minus pi halves, minus pi, 1, 2, 3, I'll put one more out here, minus 2 pi. Okay? Forgot to put those. And your vertical scale, because we've got, shifts and everything else, 1, 2, 3, 4, 5, 6, 7. You don't need that many. -1, -2, -3. Okay. I knew we were shifting up to, and that we had an amplitude that was greater than 1, so needed to have enough numbers up there. That's where you begin. Okay. Now is where the intervals come into play. At the first interval, this is going back to your equilibrium position. It used to be to your intercept, no longer intercept, your equilibrium position. Okay? Then the next one goes down to your minimum. Okay? And the minimum will be 3 below your equilibrium position. Where would that be? -1. Perfect. And then the next interval, you go back to your equilibrium. Then you go back to your max. Then you go back to your equilibrium. Then you go back to your min. Then you go back to your equilibrium. Then you go back to your max. Then you go back to your equilibrium. And going in the reverse direction, you come down on the first interval to the equilibrium, then to the minimum, then back up to the equilibrium, then back up to the max, down to the equilibrium, down to the minimum, back up to equilibrium somewhere here, back up to max, and then down. Okay, so it's doing something like this. I don't draw very well. Okay, something like that. A good old typical cosine function starting at its maximum, but its maximum is then shifted up and amplitude up. Okay, so that puts it up to 5, not 1. But because your shift is up, when it goes down 3 below equilibrium, it takes you down to -1. All right, does that make sense? The intervals are important because that's where your key points are located. Now, you're no longer on the x-axis. You're up at the equilibrium position, but just extend those up. Make sense? Any questions? All right. So that's your vertical translation, example 6. All right. Ready for the next? We've already done example 5, so I'm going to skip through this. Skip to the my darling. All right. Vertical translation. Now we're going to do some mathematical modeling. Okay, no, not that kind. Okay. Here's a table. Okay. The table shows the depths in feet of the water at the end of a dock at various times during the morning, where t is equal to 0 corresponds to midnight. So you're starting this measurement at midnight, and you find that the depth is y of 3.4 feet. Okay. Now, so here's how I picture this. The depth in feet of the water is how deep the water is from the bottom of the ocean, not the depth from the pier, okay, or the end of the dock. Not that. It's the depth of the water above the bottom of the seafloor, whatever you got down there. So it's at 3.4 feet, then it goes to 8.7 feet, then it goes to 11.3 feet, back to 9.1, blah, blah, blah. Okay. What's causing this variation? This is not Smith Lake. This is not a pond on your farm or something like that. Where must this be? Second, ocean, is that what you said? Yeah. This would be an ocean or the Gulf of Mexico, perhaps. What's going on there that makes the depth change? Different times of day. The tides, exactly. Okay? This isn't the roll count, but never mind. Okay. What determines the tides? Does anyone know? The moon is the biggest culprit. The sun contributes a little bit. And the moon is on what kind of a cycle, you might say? Moon sounds like what period of time? What unit of time sounds like moon? Month. The moon determines our month. There's almost always one cycle of the moon each month. It's not exact. It's close, but not exact. About 29 point something other days is one cycle of the moon. So it's not quite exact, but it almost is. Okay? Now, because of that, okay, every day there is, because of one complete cycle and the spinning of the earth and everything else, we go through, each day we go through basically one cycle, two cycles. You usually have 2 high tides a day and 2 low tides a day. Not always, because it's not an exact thing. Some days you may have 3 high tides or 3 low tides, but most of the time it's 2 and 2. Okay? Never have 3 and 3. It's 3 and 2 or 2 and 3. But it's always very early in the day and very late next. You might have the same. But here we have a periodic function. That was what I was getting at. Okay? Now, we have to make some guesses on it. It's not exact, okay, because other things are involved with it. But these are your tides, okay, or your depths because of the tides. The minimum depth seems to be right there, the maximum depth right there. What's the time interval between the two? These are hours. It's what?
6 hours.
6 hours. So if it's 6 hours from max to min, that means it'd be 12 hours for one complete cycle. In 24 hours, you have 2 cycles. Yeah. 2 high tides, 2 low tides a day. Any of you fishermen? Okay, fishermen know these kinds of things most of the time. If you deep sea fishermen, anyway, they go with the tides. Okay. So we see that this is sort of following periodic behavior. Notice on either side of your high tide, they're approximately equal. Either side of that, approximately equal. And that would be the low, so this is quite equal, but yeah, it's a little bit of slough in there because we're only measuring once an hour. Probably if we did at 4:05, you'd probably be a little bit higher than 11.3. But this is all we got. Okay, so that's the setup. Here's the problem. Use a trigonometric function to model the data. Okay? Now, I was just hinting at some of the things that we need to do. So let's go back to the data and see if we can model this. Okay. We said there's your max, and there's your min. So right from that, what can you almost get from it? What's the difference between your max and your min? Twice the. Somewhere here is our equilibrium position. That's the max, here's the min. Around 7 o'clock is our equilibrium position. Your maximum above that is called the go back to our 4 little letters, to our ABCDs, okay? Which of those is related to the maximum? The what? A, yes, the amplitude. The amplitude, remember, one expression for it is half the difference between the max and the min, right? Amplitude is how far above or how far below your equilibrium position, right? So let's take the difference here. What's that? 11.2. Take half of it. Half of 11.2. 5.6, exactly. So right now, first thing I can note here is the A is approximately 5.6. Okay? Now these depths are in feet, so I could put feet there. It'll just sort of mess up the look, but I think I will put it there. Okay. So that's related there. We've got our first. Okay. What is the mathematical model? And by the way, notice they said, use a trigonometric function to model the data. Okay. Now let's step back here. Okay. If this is the max, and there's the min, like I said, halfway in between will be our equilibrium. So halfway here will be our equilibrium. So this puts us real close to the equilibrium position, not right on it. So it looks like which function would you like to use, sine or cosine? Especially since you're starting real close to your equilibrium position. Which one starts close to the equilibrium position? Cosine? I thought that started different. Oh, it would be the sine. Good. Second guess is good. Okay. Since there are only two. Okay. Now, the book uses cosine, though. I just as soon use sine. So what our model is going to be is y, which is your depth, is equal to, and believe it or not, they do it this way. A, they do cosine, but I'm going to do sine. I like to do b times x minus c. This is my way, not their way, plus d. Okay? We got our A. We're 1/4 way to having our model complete. Okay. Now, what would be next? Well, what would you like to investigate next? We found our A. Got it. What's that? What do these things stand for approximately? We said that in between these two is our equilibrium position. And we said that's the amplitude above and below that was our 5.6, right? What is the actual measure of the equilibrium position? What does that relate to? Which one of those four letters? Where the equilibrium position is? That would be D. Okay? So we need to know the value of that equilibrium position. Something between 3.8 and 9.1. That's a pretty big, broad thing there. So let's go back to this. What would that be? These bracketed, and we're going to say this is minimum, that's max, then it would be the average of those two, wouldn't it? Exactly in between these two would be our equilibrium position. Well, that would be the average of those two. So how do we get the average? Add them and divide by 2. So when you add these two, what do you get? 11.4. And divide by 2? 5.7. We found our D. Ding, ding, ding. D is 5.7 feet. Okay? So we got D. We got A. We got D. Okay. Now, we already talked through and said this is our equilibrium position, and this is from equilibrium to max. Okay, going in this direction. From max, if you went another, so what is the time max here. This is, we said it's right in between these two. So what time would that be?
3 hours.
That would be what?
3 hours.
3 hours. So our equilibrium on this side would also be 3 hours. And where would that be? At 1 o'clock. So that's going to be, if that's going to be sine function, that will be our phase shift. Our actual C here, not the way the book does it, but the C here. So C is equal to 1. Does everybody see that? 1 hour. Okay? That's going to be our phase shift, because we're actually starting our equilibrium. First equilibrium position is going to be here at 1 hour. This is just before it. This is just after. Okay. Okay. Now, all we've got left is B. What does B relates to? Period. Okay. Now, what did we say the period was? Period is the time between two equivalent points on the graph, right? But we don't have a whole cycle here, do we? This is a max of min, and we don't have another max or a min listed here. But how much of a period is that between max and min? Because after this, you go back to max, and it's the same amount of time. So this time would be
6 hours.
That would be half a period. And that would be 6 hours, right? So 6 hours, half a period, what's your period? 12. All right, the period's 12. Is it already time to go? No, okay, good. Some people. Okay. All right. So your period, let's write this down, period, is 12 hours. And that makes sense. 2 cycles a day, 2 highs a day, high tides and 2 low tides, you get them twice, okay? So this is exactly, wait, did I say that right? Yeah, okay. Now, which one of our parameters relates to period? B. And how does it relate to period? Period is 2 pi over B. Okay, we know the period is 12 hours. Okay, so if we multiply both sides by B and divide by 12, you get B is equal to, is that too fast? Multiply both sides by B and then divide both sides by 12. 2 pi over 12 is pi over 6. Hey, guess what, folks? We got it. Here is our mathematical model. Walking down the gangway, okay? Y is equal to, there it is, 5.6. I won't put the feet down. You could if you wanted to. I'll not put my foot down, okay? Sine, now I like to put the B on the outside, pi 6 times, I like to put the x minus C was 1, and plus D is 5.7. Now, understand they're actually going to give a value for this. Pi 6 is just a little bit more than point. Pi is about, yeah, it's a little bit more than 0.5. Okay, so that's going to be 0.5 something another that they're going to say is your B, and then they're going to multiply that here, and they're going to say that's a if they're using cosine, they may be on the other side. Yeah, so that theirs is going to be a plus, but it's going to be something about 0.5 something. All right, so that's our guess of the model. Okay, so use a trigonometric function to model the data. You tell me what it was again. Y is equal to 5.6 sine pi 6 times x minus 1 plus 5.7. Okay. That's our model. Find the depths at 9 a.m. and 3 p.m. Now remember, our data started with 0 being midnight. So 9 a.m. will be what time? T equal, silly me. Let's go back here. This isn't an X, this is a T. Our independent variable is T, not X. Okay. Okay. Because Y and T. Okay. So here will be, change that also. T. All right. So what will be the depth? Remember, depth is Y in feet. So this will be Y is equal to 5.6 sine of pi 6 times 9 minus 1, which is 8, plus 5.7. Now, before you start punching away on your calculator, what you got to make sure, radian mode. You're in radian mode. Plugging in, what we do, 9 a.m. would be 9 minus 1, 8. So 5.6 times the sine of, now I like to do a little math in my head first, 4 pi over 3. Not that, like, we probably know what 4 pi over 3 is. You know, we could do that exactly. But you can use your calculator if you want to, because you got to multiply by weird numbers too. And then to that, add 5.7. Anyone get an answer?
6.109.
0.109? Let's go back and see if that looks like it makes sense. Say again? Oh, okay, I'm sorry, I misunderstood. Say that one more time then. 6.109. Okay, sorry. So you say that is going to be 6.109 at 9 a.m. Let's go back and and see if that makes sense. 9 a.m. That looks too big, doesn't it?
Yeah. I got something huge. I got 28 point something. So
Okay, no. Okay. This thing has got to be between plus or minus 1. And when you multiply this by it, you might get up to 5, but not much. And add 5.7, you might get 10 something. Can't get 26. Okay. Second? 9.86. That sounds too big too. I don't know. I don't have a calculator, so I don't know if I've done something wrong or what. Okay. 5.6 times the sine of, now be careful. Go ahead. Okay. Oh, I'm on the wrong page. Okay, this page. Okay. Let me do this in my head. Okay. This is 4/3 pi, right? 4/3 pi is, there's pi halves, okay. 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi is down here. So this value is going to be a negative number, right? And it's going to be negative square root of 3 over 2. So someone plugs square root of 3 over 2. Negate that. Negative square root of 3 over 2. Times 5.6. Add to that 5.7. 0.84? That sounds more reasonable, doesn't it? Okay. Okay, at 9 o'clock, 0.84, is that what you said? Okay. Feet. Wait just a second. Wait, let me go back and see if does this look reasonable? No. Oh, wait, 9 o'clock. Yeah, that's looking pretty reasonable, between 3.8 and 0.1. Okay, what was your question?
Did you say we needed radians?
Yes, be sure you're in radian. That's why I said
might be a problem.
it might be a problem, okay? First thing I said, what mode you got to be in, but
Now I got 28.1, so.
oh, that's what you got, okay? How are you getting that? Okay, you can't possibly. This has to be between 0, minus 1 and 1, okay? Multiply that by that, and it can't be any bigger than 5.6. Add to that, it can't be any bigger than 11.3. No way, okay? So,
My calculator's on something over here.
yeah.
They tripping on that.
I think it may be operator error, okay? What you get? Okay, let me watch someone punch it in that's having trouble getting it. Okay, that should work.
So,
Okay.
I'm putting in
Okay, you're
exactly what it
ready.
is over there.
Okay.
I ain't doing
So-
that. That's probably what I'm doing.
Try solving.
Okay, now you change it first.
First. Okay.
That's what I do.
Okay.
You should be in radian. Yeah, son. Yeah,
You did 5 or 6
5 or
times
6.
8 first.
times
Yeah. And plug that answer into the formula.
times 8. Ah, okay. That's it. If you don't close that parentheses, you might get some problems. Yeah. And what you get? Okay. Oh. Okay. It says one thing and it's actually the other. Okay. Anyone else not get it yet?
Yeah.
You still? Let me see you punch it in. And this fancy calculator.
I did the 5 or 6 times 8. You got 4.2. So I'm plugging in
What?
5.6.
I think you need to trash this calculator. I mean, there is no way.
How do you put
I'll do what he said and just solve that first.
And how does it get meters? I don't know. Okay. Everybody else got it? Okay. At 0.8 or something like that, 0.84? All right. That seems reasonable, especially if you look back at the data. And at 9 o'clock, it's going to be between 3.8 and 0.1. It's decreasing pretty quickly, but it bottoms out here. So yeah, 0.81 seems pretty reasonable to me. Okay. The next question, did you find out what it was?
my calculator's just going crazy.
Okay. Yeah. Demand the refund. Okay. How do you do 3 p.m.? How do you do 3 p.m.? Anybody have a guess? Second? Yes, you plug in 15. How many hours since midnight? So that would be y is equal to 5.6 times the sine of pi 6 times 15 plus 5.7. Okay? Probably some of you should do it in your head rather than using your calculator. Just kidding, sorry.
Oh, for real?
I don't understand that at all. Okay? Now, in my little mind, I would say this is 3 will go in the 5 pi thirds, Okay, 5 pi-thirds would be, isn't it? And 3 will go into that. 5 pi-halves. Okay, sorry about that. Is that right? That's, yep, 2.5, yeah. So 5 pi-halves would be pi-halves, 2 pi-halves, 3 pi-halves, 4 pi-halves, 5 pi-halves. Sign would be 1, if I'm not mistaken. So it looks like to me it's very close to 11.3.
You left off the -1.
What's that?
The 15.
Oh, I forgot to do the -1. Yeah, sorry about that. 15 minus 1. I didn't write down my whole thing. That would be 14 then. Okay, that makes a difference. That'd be pi-6 times 14, which would still be 7 pi-thirds, right? Yeah. 7 pi-thirds would be 6 pi-thirds, 1 more pi-thirds, 7 pi-thirds. Positive root 3 over 2 times this. What you get?
10.5.
7.5?
10.
Oh, 10.5. 10.5 feet. Okay. Let's go back and look at our data. Okay. It's 5.6 times sine of pi-6 times 14 plus 5.7. And because we're on a 6-hour period, this is 6 hours here, then what do we say? 3 p.m.? That would be right here. And what did we say?
10.5.
Ah, look at that. Right in between 8.7. What's
I
that?
got it right.
Whoa!
I figured out what I was doing the answer and then added,
Oh,
and it was coming up with a huge number in meters for some reason.
okay. Yeah, what was your question, Stephanie? You get 8 something?
10.8.
Oh, 10.8. What did you get?
We got 10.5.
10.5. Oh, that's not far off. Did you do 15 or 14? Okay.
Calculator's not young. He's just, this is supposed to be a $140 camera. Come on.
Everybody get it? All right. Now, a boat needs at least 10 feet of water to moor at the dock. During what times in the afternoon can it safely dock? Okay? Now, when I first tried it, did you get it, Stephanie? Okay, good. When I first did this, I thought, oh my, they're having us do inverse sines and stuff like this. We haven't covered those in class yet. Why are they doing this to us? But what they wanted you to do was graph it on a graphing calculator. Graph this function there. And then it needs at least 10 feet to dock, so that would be between, that looks like 2 or 3, probably closer to 2 in the afternoon, because this is 2, 4, 6, 8, 10. Between 2 in the afternoon and looks like maybe 5 something in the afternoon. Something in those time frames. What you do, you set this function here in your calculator, another function, y is equal to 10, and then find the 2 points of intersection. I went through all sorts of agony, trying to get this to do, and then I realized they just wanted you to do it on a graphing calculator that you just read with no agony. Okay, so, but I like agony. No, I'm sorry. So, and that's what they show in the book. Now, you say, oh, that was in the morning. But if this is a periodic function, it's going to be the same in the afternoon. And it'll be the same hours, too. They said 4.7 and 7.3. Well, that doesn't make a lot of, 14.7 and 17.3. Well, 14.7 would be 2.7. Well, 0.7 of 60 minutes is 42 minutes. So that would be 242 and 17.3. 17 would be 5, and 0.3 times 60 would be 20 minutes. No, I mean 18 minutes. So between 242 and 518 is what I got. Let's see what they got. Yep, 242 and 518. Okay. Do you see what I did there? If you use your graphing calculator and get the same thing they got in the book, that was 14.7. Well, 14 is 2 o'clock, and 0.7 of 60 would be 42 minutes, so 242. And the other was 17.3. 17 is 5 o'clock, and 0.3 times 60 is 18. So about 18. So in between those two times, a 10-foot draft boat can dock, but he got to pull away before 518, or else he's going to be grounded. Okay, and y'all wouldn't know what that's like, would you? Okay. Any questions? That was super cheating to do a graphing calculator, but it was fine. If you got it, use it. Flaunt it. Okay. Let's do the vocabulary. Fill in the blanks. One period of a sine or cosine function is one blank of the sine or cosine curve. I know what word they're looking for. It's not completely obvious. Right around the cycle. Okay, good. You're good at, what is that game that you don't talk, you have to make charades or what? No, is that it? Charades. Okay. Okay. You do well at charades. Okay. Number 2. The blank of a sine or cosine curve represents half the distance between the maximum and minimum values of the function. If you don't get that, you get hit. The what? He gets hit. What is it? We just did it, didn't we? I didn't hear what you said. You may have said it right. You're not going to say it again because I had my fist balled. Okay, no problem. Anybody? The blank of a sine or cosine curve represents half the distance between maximum and minimum values. First thing we did on this. Amplitude. Maximum, the difference between the two is twice the amplitude. You go up half an amplitude, down an amplitude. Okay. Number 3. Is that what you said? Oh, good. You get hit. Okay. Number 3. For the function y is equal to a sine bx minus c, c over b, the way they do it, represents the blank blank of one cycle of a graph of the function. Phase shift. Perfect. Okay. Number 4. For the function y is equal to d plus a cosine bx minus c, d represents a blank blank of the basic curves. Vertical shift. Perfect. Okay. And by the way, I meant to do it when we were doing on the, let's go back to this. Oh, they don't give the answer, do they? They should give the answer. All right, here we go. Let me remove some of my writing here. We didn't check our answer. Sorry about that. Let's check it. Notice how they write it. Y is equal to a cosine b, t minus c. I did the b on the outside, plus d. They put the plus d at the end of the line. So before they were always putting it in front. Here they put it in front. But there they put it right. Okay. So there's our model. They use cosine. Okay. Which means to me the cosine is going to be, it's still going to be a positive c. I mean, a minus c there because the, yeah, you're starting over there. Okay. Shift it to the right. Okay. So the difference between the maximum and minimum value is the half the distance is twice the amplitude. There we go. Amplitude of the function. So the amplitude is 1/2 the difference between those two, which we got to be 1/2 of 11.3 minus 0.1. Half of that is 5.6. Just like we got it. Okay? The cosine function completes half a cycle between the times at which the maximum and minimum depths occur. So the period is twice the time of minimum depth to the time of maximum depth, and that was half of twice 10 minus 4, which is 6. That would be 12, which implies that b is 2 pi over p, which is 2 pi over 12. And rather than leaving the pi's in there, they say 0.524. That's going to introduce some round-off error. If you left the pi in there and just hit pi 6, then we're going to not have as much round-off error as they do. Okay, so because high tide occurs 4 hours after midnight, consider the left endpoint C over B to be 4, so C is about 2.094. Okay, that's the way they do their C's. Much easier to do at 1. Okay, that made a lot more sense to me. But anyway, oh, and by the way, multiply 1 by 0.5214. Wait, that's not it. Oh, they're doing cosine. We did sine. We won't go there. Okay. Yeah, their peak would be 4 hours. Right. Let's go back to our data. Always go back to the data. Okay. Yeah, their peak is 4 hours. So do 4 times 0.524. Somebody do it. 4 times 0.524.
I got 2.096.
Yeah. And see, their round-off error sneaks in there and throws it off a little bit. But not bad. Okay? That's what they do, uses their C. Okay? Because they multiply it by B. Okay. Moreover, because the average depth is add the max and min, divide by 2, 5.7, there's your D, 5.7. So they came up with this model, 5.6 times the cosine of pi 6 t minus 2.094 plus 5.7. Because they use cosine, they have a bigger phase shift than what we did. And we factored out the pi 6, and we just had t minus 1. So much easier to work with if you can just remember to subtract 1. So, okay. And so then you just plug in 9, and they got 0.84 feet, which is exactly what we got right. And then they plugged in 15, and they got 10.57 feet. I think we got 10.6, right? Perfect. Okay. Then using a graph utility, graph and model the data, and that's where they came up with. This was the first graph, okay, and they extended enough to go at least cover the afternoon. And then they did the second one is y is equal to 10, and then they found these 2 points of intersection, 14.7 and 17.3. They're both at y equal 10, and that would be at 2:42, and this was 5:18. Same thing we got with ours. Well, no, we didn't do it. I just told you how to do it. Make sense? Now, if you don't have a graphing calculator, you could have approximated that. Okay. Whoa, that's the end of the section, and it should be. There is, by the way, a checkpoint there, and guess what the checkpoint is? You've already done. Find the sine model for the data. Ha! We did it. Okay, homework exercises include, it's almost time, isn't it? Any of the odds 5 through 11, they're all at Calc Chat. 7's at Calc View. Any of the odds 13 to 19, they're all at Calc Chat. And any of the odds, either 21 or 23, they're both at Calc Chat. Do any of the odds 25 to 29, they're both all at Calc Chat. 27's at Calc View. Do any of the odds 31 to 51, they're all at Calc Chat. 49's at Calc View. Do any of the odds 53 to 57, they're all at Calc Chat. 55's at Calc View. Do any of the odds 59 to 63, they're all at Calc Chat. All at Calc Chat. Do either 65 or 67, they're both at Calc Chat. 65 is a calc view. Do either 69 or 71. They're both a calc chat. 71 is a calc view. Do 73. It's a calc chat. And then do either 75 or 77. They're both a calc chat. 75 is a calc view. Then do 79 is respiratory cycle. 81 is a biology problem. 83 is an astronomy problem. 85 is a Ferris wheel problem. So you pick the one you want to do. You can do more than one. They should all be at Calc Chat. True false, 87 and 89. You can do those if you want. They help you see through it. You don't expect any on the test like that. 91 is a good one to look at. 93 is a writing problem, so you can do that if you wish. 95 is polynomial approximation. I'll let you decide whether you're going to do that or not. There is a project, meteorology, and if you wanted to look into that to see if that might be what you want to do your paper on, you could. Mentioning papers, I've gotten one. Out of my best class ever, and only one paper so far. Don't let it slip away. We'll start next time at 4.6. All right, good deal. Thank you. And the test can come in anytime, too. Thanks.
I want to show you one thing on my test.
Okay.
I know this is not the right answer.
Am I supposed to refrain from laughing or what?
No, you're gonna be laughing because of what my calculator's about to show you.
Got it.
So I know exactly how to put this in. Here,
Uh-huh.
I'll let
Oh, you got some
everybody
fancy calculator.
What's that?
It's wild. I'll wait for everyone to turn in there for it.
By the end of the term, but you get bonus points if you get it in early. So, sooner the better. You choose your topic. You've been in my class before. You know, you choose whatever you want. Related to trigonometry. Okay.
All right.
Did you have a question about the paper? Okay, well done.
So it's a topic on
What's that?
It's just a topic you pick and you relate to trigonometry.
Yeah.
And how long?
1 to 2 pages.
Okay.
All those instructions that are on Blackboard, under handouts, PowerPoints, and so forth. Also, that first class that are recorded, you can hear it. First or second, one of those. Good deal, second. All right, good deal.
Okay. So it's the secant of 235 degrees.
Right. Uh-huh.
So you got to do the cosine of
Right.
235 times -1, right?
Okay, wait.
And it's in degrees.
What you're going to do here, you're going to take 1 over 235 and take the cosine of that.
Okay,
So-
because look what I'm getting right here. I got this. And I was like, oh my gosh.
Yeah. That's even worse.
Mm.
No, actually, that may be exactly. No, I doubt if it is. Yeah. But what you have to do is
1 over the cosine.
1 over the cosine. And I don't know what this is doing. That's not doing the reciprocal of that because that would. Oh wait. No. See, cosine. Oh, okay. Cosine is never. Yeah, but 1 over that could be. So I don't know. I don't know what your calculator is doing. But I would do. Can it do this? 1. Are you in degree mode?
Yeah.
Okay. 1 divided by cosine. Oh, it doesn't open parentheses for you, does it? That's something to do. 235. That seems more reasonable.
And that's all you have to do, or do you need to? You don't have to divide it by the reciprocal. You do
Yeah,
1
I
over
don't know.
cosine.
Yeah. Right.
So that's probably the best way to put it on my calculator.
I don't know. It works for me.
Yeah.
Okay. Yeah. In fact,
So that doesn't look right either. I need to do it that way.
yeah, I don't know what this is doing. Let me see.
I just had to ask you. So my calculator's acting crazy.
Cosine. Where's the 1 over e?
I don't think I have one. But you can do this to make like fractions. Is that what you're talking about?
No. Okay. How you got the -1 over?
Oh, you hit shift and then this.
There it is, okay. It is doing that. Okay. Let's try it this way. Clear that. How do you do this?
You just click delete.
Oh, there. Okay. Okay. Let's open parentheses, cosine. $235. Close parentheses, and then do your shift. That doesn't.
Okay.
It's,
So I need to
it's a
keep it in
cosine
parentheses.
function. What it's doing otherwise, I don't know. It may be reciprocating 235.
And not cosine?
Yeah, 235.
Mm-hmm.
Where is that? Where's your answer?
Right here. 4.25.
That's not right either. Oh, what does the M stand for?
I have no clue.
I think that's some
Yes,
sort of
meters.
a very small. I don't know. Because let's do this. Remember those digits. Oh, they're going to show up.
Yeah.
1 divided by 235.
Yes, it's the
Yeah, that is what it's doing. I don't know what that stands for, though. It's some sort of 0.00. I don't know.
I'm about to just go get another calculator.
No, yeah. This is some sort of scientific notation. I just don't know what the stands for. I wish I did.
I'm about to go look on YouTube and see how to set it up.
Yeah. Right. Yes, sir.
I'll be a 115 class
Right.
on Tuesday, Thursday, and I'll try to figure out what we were doing today because I won't be in class today.
Okay. We're going to do the first 2 hours, finishing 19, and maybe even starting in 20. Then the next 2 hours are going to be the lab for 18, and then the last 30 minutes is the test on 18.
Do you think I can do the lab and the test now?
Say again?
I said, do you think I can do the lab and the test now for 18?
Do the lab what?
The lab and the test now for 18?
I'd have to set up the lab and do it with you. But I'll give you the lab, and you can listen to the YouTube video and probably get just about everything you need off of it.
Okay.
Because I'll try to have the computer down there and recording everything. And by the way, I'm recording our conversation.